Hello, I'm Robert Kraft. Welcome to the Experiment of the Week. Recently, I've had several requests to do a video on what science is. And you would think that as a science educator, it'd be very easy for me to tell you what science is. But it's not that easy. Science is such a huge topic, ranging from astronomy to microbiology, from chemistry to archaeology. There are so many different aspects to science, it's hard to boil it all down into one concise definition that everybody agrees on. A lot of it is intuitive. It's sort of like the difference between a mountain and a hill. We know that these are mountains and these are hills. But where's the dividing line? At what point does it change from being the tallest hill to the shortest mountain? There isn't one, or at least not one that I could find. I couldn't find any definition that made a definite line between the two. It's intuitive. We look out there, we know that the big ones are mountains, the little ones are hills. In some ways, the same is true for science, because science encompasses almost everything. There are a lot of different definitions. I couldn't find one that fit everything that I wanted, and so I came up with my own. Probably no better than anybody else's, but for our purposes today, it should do what we need. The definition that I came up with is that science is an objective and self-correcting method for gathering and organizing information about the natural world through repeated observation and experimentation. Now that may seem like a mouthful, but if we take it one bit at a time, we're going to find out that it really is pretty easy, and it's going to get us as close as we're probably going to get to encompassing this huge topic called science. The first bit we want to look at is right in the middle of our definition, that phrase natural world. Science is involved with the study of nature and the natural world, not with the supernatural. Now that doesn't mean that science denies the existence of anything supernatural. It simply means it's not in the realm of science. Sort of like cooking is not in the realm of astronomy. That doesn't mean astronomers don't cook their food. It simply means they don't spend their time looking through a telescope in search of a good salsa recipe. Well, the same thing is true for science. Scientists are not involved with the study of religions or belief systems simply because they're not part of science. The tools of science just don't apply to them. That raises more questions. What are the tools of science? What are the skills that scientists use in their work? We covered several of them in our definition, but by far the most important is observation, gathering physical evidence. Now, we tend to think that observation means just eyesight, but it can mean any of your senses. If you can see it, hear it, smell it, taste it, feel it, or if you can detect it with scientific devices, things that were invented to enhance or expand our senses, as long as you can detect it, then it's an observation. And those observations contain information that we can use to learn about the natural world. But if you can't observe it, if you can't see it, hear it, smell it, taste it, touch it, if you can't detect it with those instruments, it's not part of science, at least not now. As we detect new things, build new devices, expand our senses, then we expand the world of science. Until fairly recently in our history, diseases weren't part of the world of science. But with the invention of the microscope, we could see microorganisms, and we learned that germs caused many diseases. Getting even smaller subatomic particles, far too small to see even with the most powerful microscope, make up everything around us. Turning our telescopes toward the sky, we find that those are not only stars, there are entire galaxies out there. All of these are observations made with devices that enhance our senses. Let us see more and learn more. An important part of observation is being objective. Being objective means not letting your beliefs and expectations get in the way of your observations. Being sure that you're seeing what's actually happening, not what you want to happen. That can be very, very difficult, because if you put a lot of time and a lot of effort into a project and things don't come out the way that you expect, that can be very disheartening. But it should be encouraging, because it gives you the chance to discover something new. For example, say I am very, very interested in using red cabbage juice as an indicator of acids and bases. Well, I've got some juice for my red cabbage, and I've got a box of baking soda here. And I believe that if I put a spoonful of baking soda into that red cabbage juice, it's going to turn a bright orange. Well, up until the point that I actually do that experiment, my idea is fine. But when I actually do the experiment, when I actually put that baking soda in there and give it a good stir, then I have to accept the evidence. I have to accept physically what happens. In this case, it didn't turn orange. It turned blue-green. So my idea was wrong. But that doesn't mean it's a bad thing. That just gives me an opportunity to explore and find out why it turned blue-green instead of orange. With science, objectivity is vital. We have to keep not only open eyes, but an open mind. We have to be ready to accept things may not be like we want them. The next bit of our definition is the part that most people think of when they think of science: experimentation. When you think of science, you think of science experiments. But what is an experiment? An experiment is simply a controlled observation. For a simple observation, say I wanted to learn more about the effects of gravity on erosion, I could sit here and watch this rock, waiting for years, for decades, maybe for centuries, until finally it started to tumble down the cliff, and then I could observe what happened. That would be pure observation. But for an experiment, I become involved in the process. I control things. In this case, I can control the time span. So I can give that rock a little nudge. And wait at the bottom to see all the chips and scratches, to learn how its fall down that slope had changed the rock. But quite often experiments are much more controlled than that. For example, if I wanted to study the impact of rain on desert plants, well, I could come out every day and water some plants and not water others and measure how much water I put on each one. But that's not controlled enough. There are too many other variables. Some plants may have better soil than others. Some may be at certain times of the day shaded by a tree or another bush. Some may get more wind, pulling more moisture away. That's the type of experiment we would want to do in the laboratory, where we could control all of the other variables, and the only difference between the plants would be the amount of water. Other experiments have to be done in the laboratory because they just wouldn't happen naturally. A good example of that is our experiment with the red cabbage juice and the baking soda. You're not going to find any place in nature where there's a big pool of red cabbage juice and some baking soda just happens to fall down the cliffside into it. That has to be done in the laboratory. There's no other way. But regardless, they're all controlled observations. The next bit of our definition that we want to look at is that word repeated. It's very important in the scientific process to repeat an observation or an experiment over and over. First by the scientists that came up with the idea, and then by other scientists. Why? Well, let's take an example, a simple one. Imagine that I'm flipping a coin, and I notice that the head side of the coin bulges out a little bit. It seems to be a little heavier than the tail side. And so that tells me, well, if the head side is heavier, when I flip it, it should fall down. So when it falls down on my hand and then I turn over, the head side would be up. Well, I decided to test that idea. So I flip the coin, and it lands heads up. I've proved my idea, right? No. First off, it could just be random chance. So I need to try it again and again. So I flip it, it comes up heads again. I flip it, and it's heads again. I flip it, and it's heads again. Well, now I know I'm right, but not necessarily. The first step is for me to repeat the experiment over and over and over again. But the next step is to have other scientists repeat it too. Because there may be other things at work here. There may be variables that I'm not seeing. My idea that the head side being heavier may not be what's causing it always to come up with the head sides up. I may be flipping it in a way that it only makes one revolution. I may be doing something else that's strange. I may have a weird coin. So it's important to have other scientists try it too. And if you get enough scientists in enough places with enough coins, eventually one of them is going to have it come up tails. And at that point, something's going on. At that point, my idea has been shown to have a flaw. Either my idea needs to be adjusted, tweaked so that it is correct, or else it needs to be discarded for a new idea. That's the vital part of science, repeating over and over again. That's why science fairs are so wonderful, because even if an experiment has been done 1,000,000 times before, when you do that experiment, you may uncover some variable, some difference that nobody else ever did. Repetition is an important part of the scientific process. Once you do your experiments, once you make your observations, then you take the data that you've collected and you want to record that data in an organized fashion so that other people can use it. If you're not going to put it in a form where other people can use it, you might as well not do the experiment. The idea is to pass along that information so they don't have to rediscover the things that you've already discovered. The great scientist Sir Isaac Newton once said, "If I've seen farther, it's because I've stood on the shoulders of giants." What he meant by that was that all of his great discoveries were based on the works of other scientists. He was using their work as a foundation to build on, to take it the next step and make that great discovery. And the same is true today. All of the information from past scientists is all gathered together in places where we can get at it, places where we can use it, where we can build on it. We can use that as a foundation that we can stand on to let us see further, to let us make the next big discovery. The last part of our definition is the most important part of science, that phrase self-correcting. That means that scientists always have to be willing to change their minds if the evidence is strong enough. In science, evidence is the king. Anytime that you're making observations, anytime you're doing experiments, the physical evidence that you get from those observations and experiments, that's what forms the basis of science. And sometimes it means we have to change our views of things, or change our way that we think about the world around us. The history of science is filled with ideas that at the time seemed perfectly valid. In the past, scholars thought that the earth was flat. They thought that the earth sat still and the sun went around it. They thought that flies spontaneously generated from rotting fruit, all sorts of strange ideas, or at least ideas that seem strange to us today. At the time, they were perfectly valid until observation and experimental data showed that they were incorrect. Well, before you start laughing at them thinking that the world was flat, keep in mind that 100 years from now, people may laugh at us for believing in concepts like electricity or gravity or something else. In the world of science, things are constantly changing. New discoveries, new inventions let us see new aspects of the world around us. They change our views. And that's part of the fun, that's part of the adventure of science, is that there's always something new, something challenging being added to it. Well, that's all for this time. Have a wonderful week. It just means it's not in the realm of science. Sort of the way cooking is not in the realm of astronomer. Astronomer? Ow, ow, ow.